If your growth constant, K here, is not a positive value, but is instead a negative value, so we have like negative 0.4 or something, then we're not really going to be talking about something that's growing. We're actually going to be talking about something that is decaying, something that's getting smaller, right? So that's the same thing as having like e to the negative 2x, or any base to the negative power, right? That's going to be repeated instances of multiplying fractions or repeated instances of division, however you want to look at that. But it's going to be something that creates a function that gets smaller over time. So for example, let's just show one of those real quick. Okay, so if I have 2 raised to the negative x, I'm going to have exponential decay rather than when it was positive x, I had exponential growth. Now, exponential decay is a very fascinating topic, especially in science. There's probably lots of places where it comes up. The one that I know of the best is the exponential decay of radioactive elements. So exponential radioactive elements is a subject where we talk about different types of radioactive elements, different isotopes that do not want to stay together very well. So for example, there's different isotopes of uranium that want to break apart into two smaller atoms, two smaller nuclei, where the original mass has broken apart and a few little different particles have kind of fallen off as well. I guess we can find a picture of that. Now, what's interesting about radioactive decay is that it's possible to know the rate at which we expect things to decay, depending on the physics of the particular arrangement of particles that you have. So this is radioactive decay. You have some big nucleus, breaks apart into a bunch of other pieces. What this is showing is that these two things would come together. There would be an explosion where these two things come apart. So this one is basically like you've got this nucleus, you fire another neutron into it, it causes it to shatter apart, and it shatters apart in a very predictable way. The rate at which these collisions occur and the rate at which these things will break apart is something that can be experimentally found. And once that rate is discovered, there's a lot that you can do with that information. So for example, you can generate exponential decay curves. If you have a reason to know how much of a certain type of radioactive element was around at a certain period of time, and then you find a substance that has, significantly less than that, you're able to go to your graph and figure out the time period between it. Now, the way that gets used is it gets used primarily to you may have heard the term radiocarbon dating or carbon dating. That is where you take like a fossil and you find how much radioactive carbon is in there. You go to the exponential decay chart for that particular isotope of carbon, and you figure out, based off how much is in there, how old the thing was. Okay, so this is the entire field of archaeology was modernized in the last I'm not exactly sure, I think in the last century, by this technique of radiocarbon dating, where we no longer have to just say, okay, there's layers and those dinosaurs must be older than those dinosaurs because they're deeper down. We can actually go in and say, this is exactly how old we think they are. We think they are 300 million years old versus this one is 325 million years old. This is how we can date the entire age of our planet. It's how we can figure out so much information about things that happened before humans even ever were on the planet. Okay, so it's a very, very impressive, strong technique in understanding the world. And it comes from this idea of the exponential decay. Now, exponential decay acts exactly like exponential growth, but like I said, there's a negative coefficient there. So let's work through an example. It says the half-life of a radioactive substance is the time it takes for half of the atoms to disintegrate. The radioactive substance thorium-230 is used to determine the ages of cave formations and coral. The half-life of thorium-230 is 75,381 years. Okay, so let's think about how we can kind of put numbers into our equation here. So we have y equals a e negative k t. Well, whatever the initial amount, oops, the concept of the half-life here is that the final amount, this one, is going to be half as much. So we can rewrite this as a over 2. And we know that the time is 75,381. Okay, so across this period of time, at this particular rate of exponential decay, which we're going to figure out, some amount decays to half of that amount. All right, I'm going to take the a's out. I can divide both sides by a, and then we'll just get 1/2 equals e to the negative k, 75,381. Okay, well, we're going to go through all of our regular processes here. We're going to take the natural logarithm of both sides so that we can get this exponent down to the kind of main level. So ln of, I'm going to say 0.5 should equal negative k times 75,381 times the natural log of e. All right, so I kind of already did that step where I bring all that stuff down. If you guys recall, natural log of e is just 1. So that part goes away. And then we have our expression for k, our equation for k described pretty quickly. We can divide both sides by that 75,000 number and by -1. To get k by itself. Okay, if we do that, let's check what that is for an actual answer. So we have negative ln of 0.5 divided by 75,381. Okay, so this number is not going to have a great significance to us because we are not doing a whole bunch of radioactive decay problems. But what we'd find is that, so this is like 9 point, I'm going to call this 9.2 times 10 to the, what is that? Negative 1, 2, 3, 4, 5, 6. Okay, if you don't know scientific notation, that's just a way of writing this so we don't have to write all the zeros. Okay, so we would generate a decay rate value for this particular isotope of thorium. This would be something that would go into like a big table. We'd have 1,000 different radioactive isotopes, and all of their particular values would be stored in that chart after somebody had figured them out, so that the people who are using that could reference those values in order to solve for those time periods. So typically, all of this work has been done for the most part. So like scientists have figured out all of these rates. What would be the more likely operation to go through would be that you wouldn't know this time, and that's what you'd be solving for. You would know like the initial amount, you'd know the final amount, and you would know the rate, which had already been discovered by somebody else, and you would use those values in order to solve for the time. So that's the process of radiocarbon dating. Okay, so that is the kind of process we'd go through on example number 2.